like it was a little rough on the first day in terms of trying to grasp everything. And then the second day got a lot stronger, and I could see a lot of traction coming through the questions. And so I think Sierra felt the same thing as well. This is a hard concept to explain to people. And I think I can cast a little bit more light on it. But I wanted to do two things today. I wanted to go through numerics with gift sampling, just things that you are going to encounter. So it's just good to understand this stuff going into it, that it's not as easy as writing it all on the chalkboard when you go to a computer. So today, I think we can do numerical issues. Implementation issues. And maybe recap on mixture models. Which one do you guys want to do first? Sick of hearing about mixtures? You want to hear about numerics, or you want to get this mixture thing down? Mixtures first. Cool. Let's write it the other way. Isn't it amazing how you not sweep chalk? So, you want to know what the secret is?
Yes.
Shove that chalk into the board and hold it at an angle. So, if you go straight in and you're light, it'll squeak on you. So, if you go to the lectures, you'll notice that when I hit the board with the chalk, I hit it harder than you do. And so it kind of smashes it down and it doesn't have a funny edge on it anymore. And that's what's squeaking. So that's what I think. Saying that, I come out of class covered in dust because of it. And so there's a trade-off for that. Okay. Just get this warmed up so we can look at this at the end. But we'll start with mixture recap. I'll try to explain it the way that I explain it. And I think in terms of running code for mixtures, Sierra's got a really cool piece of code. And so I'm going to ask that if you have any more questions about it or things like that, want to see those examples, she can run them for you in a review session maybe next week. Are you available on Wednesday next week for review? Thursday?
I still have soccer. So Thursday, yes.
Thursday's your day. Okay. I can do Wednesday next week, and Sierra will do Thursday, and I'm going to do tonight as well. So we'll do a review. Tonight at 6:30 p.m. And we'll do 2 next week as well. And homework is due next Wednesday. 1 week.
Question for next Thursday's Halloween. So how many people would actually show up on Halloween? I will.
Oh, next. Oh, I see. Thursday is Halloween. Okay.
I'll show up. The people will show up.
Will you be costumed?
No.
You bring candies?
No.
I mean, it's pretty early, right? If you like do a 6 p.m. or something. If people want to see the details of the code, if you want to show up, I'll leave it up to you. You can send out to the group if you want to reschedule something. I think that's fine as well. All I want is everybody to at least be able to discuss with you some of the implementation details. I'm going to have you code this up on a homework. And so you will eventually understand it all. And we'll do higher dimensional examples and more sophisticated examples as well. And so this is almost unlimited. One of the things that we've talked about also is that we know how many mixture components there are, and we'll be studying later on if you do not know how do you do all of this. So I'll tell you what a Dirichlet process is all about. This will be the first time I've ever taught that in this class. That didn't go. Still warm enough.
Dr. Lehman, is our test still going to be on the 4th?
Yes. Why wouldn't it?
Well, then I would show up to a review session on that Thursday.
Yeah.
If the test is setting.
Probably never move a test because one person doesn't like it. You know, I suffer because of that.
Are we going to do yes, no's, and maybes before the test?
Yes, no, maybes. We could probably do that. Yeah, I could do yes, no, maybes. So what Christina is saying is that in some of my other classes, I do a review session where you get to ask me what's on the test. So I kind of got sick of the whole, you know, you guys ask, is it on the test, right? We've heard that all through our careers in school. And instead of fighting that, you know, I've decided to just embrace it and build it into the class. So what I'll do is I'll partition the board into 3 sections, yes, no's, and maybes. So you ask me, is this on the test? And I'll put it into one of the columns. And so I try not to have the maybe column super big. And so, okay.
So, can you give a simple example for the case where we have like more than 2 parameters and we want to use if sample?
Yeah.
I just want to know the steps.
So in the mixture recap, there's a whole bunch of, way more than 3. Okay, so I'll write it down just in general. Let me just say this before we begin. So I'm not even started yet on the video, but give sampling just real quickly. With 3 parameters. This is just a little bit of review. We'll get to mixtures in a moment. Say I want to sample from this distribution. From, I'll just write it down like this. Pi, theta 1, theta 2, theta 3. So 3 parameter distribution. Gibbs can be used for any distribution. Bayesians like it because they usually have posteriors that are written down. Some distributions, so again, a Bayesian always lives in this probabilistic framework. So we're just doing probabilistic inference. It's all just calculus at the end of the day. But we need to be able to sample from this. And so here's the Gibbs algorithm. So Gibbs is just this. You write it over. So Gibbs is this. It's going to run in a for loop. T is going to go from 1 to some large number. I'm going to need to initialize some stuff up here. If there's 3 parameters, we need to initialize 2 things. And so you're always going to, whatever the parameter space is, say it's p dimensional, you're going to initialize p minus 1 things. If you initialize everything, it's okay. Code won't crash. You just won't have something initialized. So I'm going to say maybe theta 2, 0, and theta 3, 0. So I'm going to initialize these. So I'll set them equal to some numbers. Okay, so like 4, 7.2. I have no idea where to initialize. Just set them equal to something. Okay, so what we're going to do first is we're going to update theta 1. So this is going to come from its full conditional. Which theta 2 and 3 am I going to condition on? The most recent values, our initial step, our initializers in the first thing. This is also going to be conditional on x, the way that I've written it out. Everything's conditional on x. We're going to sample from something conditional on x. Then I update theta 2. I sample from its full conditional. Theta 1 and theta 3 I'm going to condition on. So that's what it means to be full conditional. I condition on everything else. Which one do I pick right here for theta 1? I'm going to pick t, my most recent value. I don't have a more recent value for theta 3, t minus 1. And then we update theta 3. From its full conditional out distribution, I condition on theta 2 and theta 1. Which values? My most recent values. If you did not know how to sample from these full conditionals, Metropolis Hastings is allowed that. And so that's what it is. You might ask, does the order matter? It can, but in probably fairly trivial ways that you won't notice. And things, how you update things in blocks, though, can matter. So it turns out, where some real deficiencies could be is, let's imagine these two parameters right here were very correlated with each other. So let's imagine theta 1 and theta 2 had some weird correlation structure. And so if I'm just updating theta 1 right here, what it's saying is I can only move parallel to the theta 1 axis. So I can only move in steps like this, in this direction. So let's say my initial value was right here for theta 2. So then I'm going to sample theta 1 and it's going to be able to move this way. Now once I pick a value, let's say I pick this one on this iteration right here, and I'm going to update theta 1. So just ignore theta 3 for a moment. Just think about iterating between these. Then I can only update in that direction. And so the Gibbs sampler only allows you to update in axis parallel directions. Right here. What you could do if you ended up having something like this, where this is heavily correlated, it would take you a long time to move from this end of the space to that end. Obviously, being able to sample the eventually part in a Gibbs sampler, converging to the stationary distribution, means that I'm able to sweep through the distribution and get samples in all the high probability spaces. This might get a little bit bogged down because I'm only able to move in these two directions, but I want to move in the diagonal direction. So what some people will do is they might say block update these. And then you might want to, instead of sampling from theta 1 and theta 2, so there's all kinds of choices and strategies, you could say, I'm going to take theta 1 and theta 2 from its joint full conditional. So what you might do is say, I want to sample these jointly right here. That gets a little bit harder. You might not know what that joint representation is. But what that allows you to do is sweep in these diagonal directions, back and forth. That way, if you're able to update them together, know how they're associated. So what people will sometimes do is they might say, hey, I know how to sample from all of these things. Right here, I know how to sample from that, that, and that. I could run a Gibbs sampler, but it can be advantageous to block update these and use an imperfect sampler, Metropolis Hastings. So you might say, I know how to sample from these, because they're all maybe exponential family distributions. I've got a button on my computer that can do it. But a joint updating I don't know how to do, but I can bury in Metropolis there, and now I'm allowed to propose in these diagonal directions. So I need a proposal that can push me in those diagonal directions. How would I know which direction to go? What you typically do is you run your sampler for a little while, you see where it's trying to move around. And then you might say, well, I'm going to build another proposal that kind of has this correlation structure to it. There's a lot of packages out there that try to do this automatic adaptation for you. I'm not going to teach you to do any of that, but anything I tell you to do, you can imagine training a robot to do it. And so this would be a strategy as well. This would be a Metropolis within Gibbs sort of thing. It's a Gibbs sampler. I could have updated this one first and then updated those. And you can block update however you want. And so that's really what goes on under the hood when you're building your Gibbs sampler, is figuring out what do I want to update together and what do I want to update independently. And so, and the answer to that has to do with whatever the answer to the problem is. What is pi? And that's what you're trying to learn. So a lot of times you run it, you build a clunky sampler, it doesn't work that well, you use kind of a clunky proposal to do it, and then you say, oh, I'm going to improve my proposal so that I can speed this thing up. And so it's neat to have strategies that can kind of sort themselves out and be very flexible. those sort of strategies, you always pay a computational price. And so you want flexibility, it'll take more time. If you know something about the problem and you know how to design a proposal, then you'll be able to sample quicker. So that's really the practicalities of it, and that's why I can't ever tell you exactly what G is going into a problem. I have to work on it and figure it out. There was a question?
Yeah, how much longer will Gibbs take to converge if you have embedded metropolises?
It depends. So, right, it could be faster. So in this example right here, this could, if these were highly correlated, super correlated, and this distance right here was very far from that, then running the Gibbs thing would be slower than maybe Metropolis with a really good proposal. And so it's really a question of how correlated are the parameters is the answer to that. And so it could go faster or it could go slower. So if it was always, it'll go faster, then I would teach you that. And so this is algorithmics at its finest. It depends on what we're looking at. So all these sorting algorithms you learned once upon a time, it's like, which one is better? It depends, was the answer. If you've ever taken a data structures class or something like that. And so, but it depends on what pi is. And so if I did this sort of thing and I had a proposal for doing this in the Metropolis thing, and it barely moved my proposal, then it would take a long time. If I had a proposal that was close to my target, then it would be pretty fast. Depends on G, depends on how I've tuned it, and it depends on its relationship to pi. All things you don't know going into a problem. So we've got algorithms that are kind of easy to run, that we can get kind of a semblance of convergence, and then we've got strategies for making it go faster. So a lot of times people, you know, when they're running all this, they have a well-designed Metropolis algorithm. They didn't have that just starting out. You know, it probably took them 3 months to get that thing tuned well, and strategies for walking through space. Saying that, for our problems that we're studying right now, we're going to set them up to be at least a little bit simpler so that you get convergence quicker. Okay. Any other questions about this? Get my head straight. Think about how I want to do this. Is this the notation that was on the board last time? Is this it? Same notation? Okay.
We used normals, I guess, instead of fx of knowing that though. So it was phi 1 times normal of mu phi. Are we
Yeah.
talking about Sierra's session?
Well, how it started out. Yeah.
I
Used a lot of
just
things,
use
but
normals,
yeah,
but
but
here
in the
he's keeping
first-
it more general.
In the first part of the lecture, that was written down, right? And then it changed, I think. Two component mixture. Okay. Let's begin. So from last time, I'm gonna go back about an hour in the lecture. Sierra did a good job of explaining, you know, her Gibbs sampling code, but I want to put a little bit more notation on this, so if any of the steps are confusing. So she started out with a two-component mixture model, and this would represent the two components. This right here is component one. And this is right here, component two. This right here is the probability of being in component one. And similarly, this is the probability of being in component 2, right here. And so Sear gave you an algorithm for sampling from a model like this. So when you get an X, it came from component 1 or component 2. And what Sear told you is these can be wildly different distributions as well. You can mix any distributions with each other. Just keep in mind, right here, this is a distribution. How would I verify that?
Integrate.
Integrate it. And it has to integrate to 1. So we know that each one of these things, if they're density functions, if I integrate over it, they integrate to 1. That will integrate to 1. And Sear gave you a constraint saying the pi's sum to 1. And so I'll write down pi 1 plus pi 2 is equal to 1. By virtue of them being probabilities, these pi i's are also positive. So pi 1 and pi 2 are probabilities, so they're greater or equal to 0. I wouldn't put in that they're equal to 0. That would compress this to a 1-component model. So let me just extend the notation a little bit. And I'll write down a K component. I think Sierra wrote down a cap C component mixture model. So we can stick with that. So a cap C component mixture model would have this form. Pi I F X given beta I. So these, what I'm kind of representing, if my F's are the same function, then this has the same mixture components for every component. Technically, this could be different for each component as well. It could be a different function. I'm just going to assume all the F's are the same. But you have that flexibility to make them anything you want, and there's very good reasons to do so sometimes. And the example that Sierra was showing you were that these were normals right here. That's at least the examples you're going to be coding up for your first round on homework. So this will go from 1 to cap C. So that is a cap C component mixture model. I want to put a little bit of labeling on all of this. I want to be a little bit more superfluous about this. I want to write down that each one of these has a component label. Label. Right here. This right here is going to be the probability that Ci is equal to one of the component labels in here. So in our example with 2 components, this would either be a 1 or a 2 right here. So this one is that this X, let me actually write it down like this. C is equal to I. I'm going to write this down that C is equal to I. Those explicit components. I want to give this a little bit more notation right here. That I'm going to get some X out of this. So I'm going to sample from this. So the question is how do you do this sampling? There's 2 steps. So let me write down the 2 steps.
Just to avoid confusion, I guess it's really to change one of those C's.
Yeah, you're right. Not cap. So this is just little c right here. So 2 steps for sampling X. So step 1 is I'm going to flip a coin with these probabilities on it. So this is going to be a cap C sided coin. So how do I do that? What is that called? What's that process called? Flipping a multi-sided coin? Binomials the two case. Multinomial. So what I'm going to do is I'm going to sample C. C right here. And this is going to come from a multinomial. And these have some probabilities attached to them. They're the pi's. Pi 1 down to pi cap C, number of components. And so once I know which component I'm in, then I sample from its respective distribution. So step 2, I'm going to sample X. Now from F, X, given theta, which one do I want? I want whatever that number is right here. So I'm going to write down C, not cap C, just whatever this is. So that's going to go right there. So that's the theta that I'm going to use to sample from. And I'm going to be even more superfluous about this, and I'm going to write down that I get to know what C is. Okay? Because that's really what I've used. And so it seems like extra notation to just build it in. I like this extra notation, just to remind me what I'm actually conditioning on. So somebody help me out right here. This is a joint sampler. What is the joint distribution that I'm getting out of this?
Pi C and of X given theta C.
Yeah, but what are the draws that I get? So we get a joint draw. It's really these two steps. I get C and I get X. So this produces a joint sample X and C. Okay. That's what we get. So C is a random variable in all this. So what we're not going to let you see in a real problem is what the C's are. We're going to take them away from you. But let's discuss if I actually gave them to you for a moment. Christina?
Here, are we actually saying that cap C is random, or is it C that is random?
C is random. Cap C is fixed. So this is fixed.
So what if cap C is not fixed?
Then I need to tell you other things. So I'm going to assume you know what cap C is right now. So what you could do if you don't like that is you could take everything that I give you, plug in different cap C's for it, and then do a likelihood ratio comparison of some sort. You probably want to penalize for the different dimensionality, and so you could do some sort of offline model selection to decide what cap C is. Now I can understand you saying, I don't want to do that because I need to run all these models out there. And so I really want an algorithm that also co-estimates what cap C should be. I'll give you that in a few weeks' time. Okay, so this is called a finite mixture model, C component, or finite mixture model. And that's explicitly saying cap C is finite, and we know what it is. Okay? So if you had good physics in the problem, you understood what was going on. CRE used examples like we want to control for boy-girl populations. That kind of makes sense. So maybe you're saying, I want to look for two different populations out there. Only issue with that is you probably know who boy-girl is in an example like that, but there's sometimes missing substructure. So I go to a hospital and I genetically like another group that responds well to a certain medication, and they don't know which one it is yet. And so they don't know what my labels are. And so the doctor's job will be to figure out what my label is, and then what the intervention strategy is, i.e. which betas will it give me for that. So, but you're right, most people need to estimate that somehow. I'm going to assume for this lecture you know it. Okay, so you actually get a joint sample from this. And so let's just say I gave this to you, the x's. Let's say we did this a whole bunch of times. Sorry to change my indices. That's usually an I, and that's sometimes a K in a lot of literature. But I'll say J goes from 1 to cap j. This is usually cap n. So I'm going to do this a whole bunch of times right here. So I'm going to just make sure that I label all of this with some j's in here. So I'm going to get the j1, then I'm going to condition on cj. That cj will go right here, and then I'm going to get the j draw. So, and this is going to be j. Okay. And I'm going to do this a whole bunch of times, and I'm going to get a lot of data out of this, and those are those representations that Sierra saw. So, showed you. So, she showed you some histograms, maybe with something like this. So, let's just say cap C is 3, something like this. So let's say that's actually what it looks like, and then I just run through this cap j times, and I get a lot of samples in here, and I get a histogram representation of this. And I also, this is just my x's right here, so this is our mixture. These are my x's right here, so I'm just plotting those. If I gave you the c's, estimating everything is pretty easy. So note, if I gave you c's, C1, C cap j, estimating theta 1 to theta cap c would be relatively easy. So I mean relatively easy, easier than if I took the c's away from you. Let's do an example real quick. So imagine c was equal to 3. And we've got normal mixture model. So what I would have is pi I sum. And then I would have normal x given mu I, vi, the precision parameter, and I'm just going to write down that we also happen to know that c is equal to I in here. So that's what we'd be doing. So we're flipping a three-sided coin, deciding which component we come from, then I draw from that relative normal. Let's imagine my draws look like this, right here. And let's say I gave you the c's. You observe x 1 to x cap j and c1 c cap j. Let me just ask you the question. How would you estimate keep it simple. Ask you one thing at a time. How would you estimate mu1 if I gave you that data?
You would just use the normal Bayes estimator on that subset.
Okay, so which Bayes estimator do you want to use?
So x bar.
Okay, so you have an L2 loss function, you just told me. So you told me your loss function, you gave me your priors, so I'll interpret. You've got some priors on mu that were flat. So x bar, so I just average all of these together?
Just the subset associated with C1.
Thank you. Yeah, absolutely. So what I would do is I would just look at the, I'll just say x, cap x, C1 is the x samples, xi's, I'll say xj such that cj is equal to 1. So these are the x's such that their corresponding c so that's what this says. This usually says something like, here's the set right here, and here's the condition on my set. So Dan might write something down like that.
Is it C is equal to J or CJ
Sorry,
is equal to 1?
These are the xj's. I just want the xj's right here such that the cj is equal to 1. So I get a pair. This x, x1 goes with c1. I want to check to see the ones that are coming from component 1. That's all that says. So it's the x's from component 1. So what we'll do right here is we'll take these and we'll average them together. Average these. To get mu1 half. Okay, so that would be my estimator. And so it doesn't matter what the other ones are. They're samples from some other distribution. I should not use those samples to estimate what's going on in component 1. So I shouldn't use samples from component 2 or 3 to estimate what's happening in component 1. That would just be a mistake. And so if I asked you the question, how would you estimate phi1? You'd probably give me the standard estimator that we came up with for phi1, maybe the expectation if you're working in L2 loss. We'll get to what all that decision theory mumbo jumbo is about. But we'd probably estimate it just like we did before, but we'd only use the data points coming from that component to do it, so on and so forth. So the problem's pretty easy if you know C's. So learning the C's is pretty easy if I know the parameters. So let me just write this down real quick. Learning theta i's is easy if we knew C1 all the way to Cj, if we knew the labels. So if I told you that, not too hard to do. Just estimate those parameters in that distribution using your favorite Bayesian set of priors, however you want to go about business, maybe reference priors, and just do what we've learned for the last month and a half. And so, also, learning theta i's is easy if we knew, oops, I'm doing this the wrong way.
C i's.
Learning the C's,
CJ's.
J's is easy if we knew thetas. Let me show you in this picture. So let's imagine this is mu1. That's sigma 1. This is mu2. That's sigma 2. This is mu3 given sigma 3. Right there. Imagine I saw this data point right over here. Which component do you think that came from? 1. So anybody could tell you that. What if you saw the data point right in here? probably, if it's pretty close to mu relative to the other, this mu1 relative to that, so if it's closer to that with respect to its standard deviations, then you'd probably think it belongs to that component. If I gave you this data point right here, one right there, which component do you think it came from? 2. So here's where things get a little bit tricky. What if we ended up seeing this right here? A data point right there. It's probably 1. And so JB's got a good eye for that. JB, what about right there? Harder to do. So why was he able to say this is almost in the middle? So if I looked at that right there, and I looked at the middle right here, this is about equal distance between the two things. So JB accounted also for the variation in the distributions. So that one has a little bit more variation. The tail's coming over there a little bit more. So it's probably almost certainly 1. It's not just because it's in the middle. Okay. And so things get really hard when you get right there. Nobody knows. And so obviously there's some joint uncertainty with these labels and being able to estimate the mu's. If I give you the label, you can tell me what the parameters are. If you tell me the parameters, I can probably tell you the labels. JB was just doing that. And so let's just figure out how we do that.
What do we mean by joint uncertainty?
Uncertainty in C's and uncertainty in all of your model parameters. We want to co-estimate that. You're jointly uncertain about those things. And so a lot of these questions that I heard, like, why don't I just put in my, whatever I think the cluster label is? So run k-means or something like that. That was a common question that came out of the last 2 lectures. You could. And you're saying you know what the labels are when you do that. Saying that, there's uncertainty with that and what you're truly trying to estimate. What are the model parameters? So we want to model those together.
But if we're saying that it's uncertainty on both the CJs and the theta, but we're actually saying that we know the theta or we don't?
Yeah, I'm saying that in these 2 steps, that if I knew one, the other thing is easy to estimate, but we don't know either one. And they're both highly related to each other.
Oh.
So that's what I mean by joint uncertainty. Make sense? You can see I'm setting you up for Gibbs in doing this as well. Okay, let's just see how we do this. So, question, given beta i's, I'll say this, mu 1 given theta i's, I goes from 1 to cap c. In our case, this is 3 for our example. How do we find probability of Cj is equal to one of these numbers right here? So the probability of Cj being equal to something given everything else. So if I know everything else, model parameters, and data, that's what I mean by everything else, how do I figure out what this probability is? So this right here is saying xj came from component I. That's what that says. So xj came from component I. That's the label. So I get to know what x is when we do all of this. And so the question is what do we need to know? What do we actually need to condition on to figure all of this out? Figure out what this probability is. How many x's do I need to know to answer this question?
It depends.
If I gave you the thetas, does it?
Then you don't need the x's because
you-
you know the model.
Right. So how many x's? So again, this is a question about xj. Do I need all the other xj's to figure this out? All the other ones, minus that data point. So I get to condition on everything in the model. How many x's do I really need to see? I think that the answer is only one, and there's a reason why, because I also know the model parameters. So all of those other x's can only go into estimating those model parameters. But since I'm giving them to you, you don't need to know them. And so again, it was just like what we did with JB right here when I said, where do you think that came from? JB didn't say, show me all the other x's. And I'll tell you, all the other x's just define the shapes. But I'm showing you the shape because I'm telling you the model parameter. And so he only needed to see one to answer the question. And so I only need to condition on 1x. Only need xj since we have the model parameters. Theta i's in here, the mu's and the phi's. Okay. So let's write down this probability then. So this is going to be probability of Cj is equal to I, given all of my model parameters. So this is going to be my mu 1, mu 2. Let me write it this way. I goes from 1 to 3. These I goes from 1 to 3, so this is the set of all mu's. This is the set of these right here. And I get to know xj. So set of mu's. Set of precisions. So we've already ascertained we only need one of the data points to answer this question. The other ones are totally uninformative. And so how do I get this? One thing we know is this. Fx given theta I Ci right here. I'll just leave it as C. So we know this. In our example, this is a normal. So this is going to look like 1 over 2 pi, root 2 pi. I've got a phi in here. So I'll write this down. Yeah, I will. I've got my phi for this thing. It's going to be phi I, e to the minus phi I over 2 x minus mu I squared. So that's what it is. Notice there's no c in here in this formula, but when I write it over here, I'm prompted to do a Bayesian analysis. I want to build a probability measure on this, and I have something that's conditioned on it. And so I only know 1 gig in town from moving from what I'm conditioning on to the random variable. How do you do it? It's this magic wand. Bayes. So the only strategy in town for upgrading your conditioned on variable to a true random variable is Bayes' theorem. And so how do I get this right here? For our example, we're just going to write this is proportional to 1 over 2 pi right here. I'm going to have phi I e to the minus phi I over 2 xj minus mu I squared. And I need to normalize it. So that's where I use all the other parameters. This is relative to something. So here's my normalization constant. So this is going to be I goes from 1 to 3. That's how many components I have. This is going to be phi. And I can change this if you'd like, but I'm using I redundantly. So let me just let that be a k for the time being. K over root 2 pi e to the minus phi k over 2 xj minus mu k squared. And then I need a prior times my probability that Cj is equal to I. This is my prior. And I need to put the prior, multiply that in to both the numerator and the denominator. So apologies, I just wrote down the likelihood functions. So multiply by my prior and normalize. And there's 3 component labels. Let's pick up on this step next time. Go back through this, and then we'll get into the numerical issues. But this is what Sierra was explaining to you. It's just Bayes' rule, and it's real easy if you put the C over here. So then I do this for every data point. I figure out what its component labels are, and then we update the thetas accordingly. I iterate between these two things, and what do you end up getting? You get the joint distribution of all the C's and all model ranges. We'll pick up with that next time. Thanks, you guys.